All right, guys, so 13G is all about the relationships between lines. So now that we've talked about, again, refreshing how to find the points where two lines intersect, let's actually see, do they intersect or can they intersect when they're in two-dimensional space and three-dimensional space? So how do they work with one another? So with our first example here, we've got two-dimensional vectors. So they're in one plane, and they could either intersect, again, or they could be parallel to each other, so no intersection, or coincidence, just being there are the same exact line. So they would have every single point in common. So with one point of intersection, yes, they would intersect. They would have one solution. If they wound up being parallel, they would have no solutions, so they would never intersect. And again, the way that we check parallel lines is if the first one is equal to the second one by a scalar. And then if they're coincident, they have infinitely many solutions, so they would have the exact, every single point they would wind up sharing. So many, many solutions. And yes, we would be able to set them equal to each other. This coincidence or parallel is also if you found the angle between them, you'd find either 0 or 180. Whereas with intersecting, we would actually find an angle between them. Now, the game changes a little bit when you guys go into three-dimensional space because you could have two lines that are in the same plane, so then they would intersect and we could find the angle between them by using the dot product and the cosine theta formula. If they're parallel again, we'd look for 0 or 180, or if they're coincident, then they wind up being the exact same line, so we'd have to show that they actually do have points in common and they actually are parallel to each other. Whereas if they were parallel to each other but they don't have any points in common, then they were just parallel, not coincident. But then because you have three dimensions, you could also possibly have lines that look like they're intersecting, but they could be in two different planes and therefore they are skew. So in other words, they might look like they're intersecting from one vantage point, but then as soon as you look from another view, there might be some space between them. So one of them might be sitting up, moved vertically in the Z direction, whereas if you're looking at it straight on, it might look like the two lines are intersecting. So you could still find an angle between them though, but you would notice that they would never intersect. So you wouldn't find an intersection point, but you would be able to find an angle between them. So again, just take a look at what the directions are asking you guys to do, or if it's a situation or a scenario, see if you can draw a picture first or get a mental picture of what's going on so you know what you're actually testing for. So for the two examples that we're going to go through in this video, we'll look at 3D vectors. Line 1 is given to you, line 2 is given to you, and it says show that the lines are parallel but not coincident. So in other words, they are parallel to each other, but they do not share any of the same points, so they're not going to be the exact same line. So we need to show two things here. So if they are parallel, first of all, we need to show that by using their velocity vectors, or the direction vectors, they actually are equal to each other by a scalar. So in other words, we will take let's see, this one, and set equal to this one by a scalar k. So let's take 2, -2, and 4, and we're going to show that that is equal. Oops. All right, so they are equal to each other. So the 2, -2, and 4 is equal to the -1, 1, and -2. So they're direction vectors by a scalar. So again, if we just look at the first x component, 2 equals -1k. K would equal to -2. And let's just see if that actually works. -2 equals -2 times 1, yes, and 4 equals -2 times -2. So yes, they are parallel. Okay, because they are equal by a scalar. However, second, we want to show that they are not coincident, so they actually do not have any points in common. So for that, we're going to set our components equal to each other and show that we actually would not wind up finding any of our parameters that match up. So -1 plus 2s is our x component for line 1. We want to set that equal to 1 minus t. Make sure we note that's an s, not a 5. And then 1 minus 2s is equal to t. And then 1 plus 4s is equal to 3 minus 2t. All right, so go ahead and pause here. Try to solve these three simultaneous equations for s and t, and note that you are not going to, it's not going to work out as you would think it would. So you're not going to find a t or an s that will make these three equations true. Go ahead and pause here and try it, and then you can check with my work as well. So what we start to notice here is if you solve for t, it equals 2 minus 2s. And then here we have 1 minus 2s is equal to t. So if I substitute 2 minus 2s in here, and I add 2s to both sides, we're going to wind up with 1 equals 2. So that doesn't work. And then here if I solve for t, so I subtract 3, I'll get negative 2 plus 4s equals negative 2t. And then let's say I divide by negative 2, so t equals 1 minus 2s. So again, if 1 minus 2s is equal to 2 minus 2s, we run into the same problem here. All right, so what winds up happening here is that you cannot find an s and a t that will actually work. So there is no intersection. So therefore, if there is no intersection, then they are not coincident. All right, and therefore we have satisfied this question. We have shown that they are not coincident and they are parallel. For our last example, you're given 3 lines in 3D space, and it says to show that line 2 and 3 intersect and find the angle between them. So they are telling us that lines 2 and 3 do intersect. We're just supposed to show that they do intersect and then find the angle between them. So in order to show that any lines intersect, we're going to set each of the components equal to each other. So let's start with the x components. So 1 minus t we'll set equal to 1 plus 2u. And then the y component, so we'll take t and set that equal to negative 1 minus u. And then the z component, which is 3 minus 2t, and we will set that equal to 4 plus 3u. So again, let's start this one like we did the last one. Try to solve for u and t and see if you can actually get one value of u and one value of t that will satisfy all 3 of these equations. So go ahead and pause here, try to work it out, and then you guys can push play and check with my work. All right, guys, so for the x components, we get down to t equals negative 2u. So I used that and subbed it into the y component, and I was able to find that u equals 1. And then if u equals 1, I can find that t equals negative 2. And then just to verify, you can sub the t and the u back into the x component, and those wind up equaling negative 2, both sides. And if you sub negative 2 back into line 2, you'll notice that the position of line 2 when t equals negative 2 is 3, negative 2, 7. And the position of line 3 when u equals 1 is 3, negative 2, 7. So they wind up being at the same point with those respective parameters. So yes, they do actually intersect. All right, now our second job is to find the angle between them. So we go back to using our cosine theta formula, which is your dot product. So I'm going to take vector 2 and dot it with vector 3, our velocity vectors, and then we'll wind up taking the magnitude of line 2 and the magnitude of line 3 of our velocity vectors and multiplying them together so we can find our theta. So for this one, we wind up with just looking at, again, your velocity vector. So we're using the negative 1, the 1, and the negative 2 with the 2, the negative 1, and the 3. So what winds up happening here is I'll take negative 1 by 2 plus 1 by negative 1 plus negative 2 by 3. And then our magnitude winds up being 1 squared plus 1 squared plus 2 squared, so that's 4, multiplied by 2 squared, so that's 4 plus 1 plus 3 squared, which is 9. So what you guys should wind up with, if you simplify that down, is negative 9 in your numerator, and then the square root of 6 and the square root of 14 in your denominator. All right, and again, if we do inverse cosine, so that we want to find our theta, so inverse cosine, of -9 over the square root of 6 by the square root of 14, and we should wind up getting about 10.9 degrees. All right, so 10.9 degrees or 169 degrees. Again, you've got two angles that make up when you have two lines that intersect. So you're looking at, here's one line, here's another. You got this 10.9 angle, but then you also have this 169 angle here, okay? Now, for part B, it says show that line 1 and line 3 are skew. So in order to show that lines 1 and 3 are skew, we're going to start the same way, and we'll set the components equal to each other. And what we'll wind up finding is that we cannot actually identify an S or a U as our parameters that will make those equations true, that will actually give us a shared point. So they will not wind up intersecting if they are skew, but we could still find an angle between them. That is a possibility. All right, so we'll go ahead and set this one up the same way, and then we'll let you guys try to finish that one out. All right, so what you guys are seeing here is that we have the x component for line 1 set equal to the x component of line 3, the y component set equal to each other, and the z component set equal to each other. And I'd like you guys to work through this, but what you'll notice is that nothing is going to work out. So your u and your s's, you will not wind up finding a value for either one of them that will actually make these three work. Again, proving that they are skew. So as a summary, again, for lines to be parallel, they need to be equal by a scalar. For them not to be coincident, they cannot share a point. So if they are coincident, then we actually need to make sure that they are set equal to each other, and we will find a point in common. If they are not parallel to each other, there's no point of intersection, we can still calculate an angle, but then they would be skewed. And a lot of these questions wind up being in three-dimensional space just because you have that possibility of the lines being skew, and it makes it a little bit more interesting. But same idea goes for our lines in two-dimensional space. All right, guys, go ahead and finish out this example for part B, and we'll start with this when we see you guys in class. Have a wonderful evening.